Welcome to the deep dive. Today, we're diving into the world of database systems.
Ooh, fun.
You want to get a solid grasp of how they work, from the basics to what's cutting edge.
Right.
And you've given us some really interesting stuff to dig into,
Yeah.
including parts of database system concepts, the 7th edition.
Nice.
We'll be your guides, helping you connect the dots and uncover the fascinating world of data management.
A fascinating world for sure.
And trust me, it gets really interesting when we get to big data later on.
Oh, yeah. Big data always shakes things up.
So to get started, what exactly is a database?
It's basically like, at its core, an organized collection of data.
Okay.
Stored and accessed electronically. Think of it kind of like a massive, well-structured library.
Oh, okay.
Where everything's carefully categorized and indexed.
Like a digital library.
Yeah, exactly. So you can easily retrieve the information.
Okay, so it's not just about storing data, it's about storing it in a way that makes it usable.
Right. And that's where these database management systems, or DBMS for short, come into play.
DBMS.
Yeah, DBMS, it's basically the software that acts as the librarian.
Yeah.
And it manages all aspects of the database.
Like the overseer of the whole thing?
Exactly.
Yeah.
It allows users to interact with the data,
Okay.
do all sorts of things like adding, deleting, or modifying information, and to make sure everything stays consistent and secure.
So it's like a control center, making sure the data is well maintained.
Exactly. It handles all those complex tasks.
Got it. Now, I know databases use data models to structure the information, right? Can you tell us more about that? What are they exactly?
So data models are essentially like blueprints for how the data is organized within a database.
Okay.
And they define the relationships between different pieces of information, and they provide this framework so you can store and retrieve data efficiently.
Like different systems for different types of data?
Yeah. Think of it like different types of filing systems.
Yeah.
Like some are better for documents, others for photos, and others for financial records.
That makes sense.
It's kind of similar. Different data models are optimized for different types of data and applications.
Okay, so it's about choosing the right model for the job depending on what you're working with.
Exactly.
Now, I know there are different categories of data models, like relational, object-oriented, semi-structured.
Yeah.
Are they all equally popular?
Relational is by far the most widely used.
Okay.
It's probably the one you encounter most often, too, in everyday life.
Interesting.
Think of spreadsheets.
Oh, yeah.
They use tables with rows and columns, right?
Right.
That's a fundamental concept in the relational model.
So each row in a table represents like a specific record,
Right.
like a student in a university database.
Exactly.
And then each column would be an attribute, like their name or ID number.
That's it. And the relational model is so powerful because it lets us establish relationships between different tables using keys.
Okay.
So we can ensure data integrity and avoid redundancy.
That makes a lot of sense. So how do we actually communicate with the database and tell it what we want to do?
Well, that's where SQL comes in.
SQL.
Yeah, structured query language.
Oh, I've heard of that.
It's the most common language for interacting with relational databases.
I see. So it's like a way to talk to the database.
Yeah. Think of it as having a conversation with it.
Interesting.
Asking it questions, telling it what you want it to do.
So instead of like manually searching through all the data ourselves, we can use SQL to just specify exactly what we're looking for.
Exactly. And you can do a whole range of things with SQL. It's not just retrieving data.
Oh.
You can define the database structure.
Okay.
Like creating tables and columns, insert data, update it, delete it, and even control who has access to different parts.
Wow, that's a lot.
It's super versatile.
So it's really more than just retrieving data.
Right.
It's about managing the whole system.
You got it.
Okay, that makes sense.
One of the key features of SQL is that it lets you enforce data integrity using these things called constraints.
Constraints.
Yeah, they're essentially rules that ensure the data makes sense and stays consistent.
So like if you had a database for a library,
Right.
you wouldn't want a book entry without a title.
Exactly.
So you'd use a constraint to say that field can't be empty.
That's the idea.
Oh, that's a good example.
So that every book record has a valid title.
So constraints are like safeguards, preventing errors or inconsistencies in the data.
Exactly. They help to maintain the quality and reliability of the data in the database.
Now, I remember seeing something about primary keys and foreign keys.
Right.
Are those related to constraints? They sound a bit technical.
They are related, but they're also fundamental to how we establish relationships between tables in a relational database.
Okay.
Think of it like this. In a library, every book has a unique ID number, right?
Uh-huh.
That acts as the primary key for the book record.
Oh, okay.
making sure each book can be uniquely identified.
So the primary key is like a unique fingerprint for each record in the table.
Precisely. And when you want to link two tables, like books and borrowers, you use foreign keys.
Okay.
So say a borrower takes out a book,
Mm-hmm.
their library card number, which is unique to them, would be recorded with the book's ID number in a separate borrowed books table.
I see.
That library card number would be the foreign key.
Okay.
It links the borrowed books table to the borrower's table.
So the foreign key creates a link between two tables based on shared information.
Right.
In this case, it links the borrowed book record to the specific person who checked it out.
Exactly. Foreign keys are essential for maintaining those relationships and ensuring data integrity.
This is all starting to click into place. It's amazing how these seemingly simple concepts can create such powerful, interconnected systems.
Absolutely. And what we've talked about is really just scratching the surface.
Wow.
SQL has way more features and capabilities,
Really?
like things called views, which are basically virtual tables based on queries. And then transactions, which ensure a series of operations are treated as one unit of work.
Mm-hmm.
So either all of them are completed successfully or none of them are.
Oh, so it prevents errors.
Exactly.
Yeah.
Crucial for maintaining data consistency.
It sounds like SQL gives you so much control over how you manage the data in a database.
It does. And it gets even more interesting when we start talking about how to visually design these databases.
Okay.
Using tools like entity relationship diagrams or ER diagrams.
Interesting. Before we get into that, what are your initial thoughts so far? I'm kind of blown away by the power and flexibility of SQL.
Yeah.
It's amazing what you can do with just a few lines of code,
Right.
from defining the database structure to setting up complex relationships and making sure the data is accurate.
Yeah. SQL is incredibly powerful. It really is.
And you're right, there's a lot more to explore.
For sure.
I'm actually curious about those visual representations you mentioned.
Oh, yeah.
The entity relationship diagrams. I'm a visual learner, so that sounds right up my alley.
Perfect. That's a great segue to the next part of our deep dive.
Okay.
Entity relationship modeling basically lets us create a visual roadmap of the database.
Okay.
It's kind of like drawing up a blueprint before you actually build something.
I like that, the blueprint analogy.
And I think you'll find it pretty intuitive and insightful.
Awesome. I'm ready to dive into the world of database design.
Let's do it.
Okay, so let's talk about this visual blueprint idea.
Yeah.
How do entity relationship diagrams or ER diagrams actually help us design a database?
They're a great way to map out the structure of a database
Okay.
in a way that's easy to understand, even if you're not super technical.
Right.
They use these simple symbols to represent the different parts of a database,
Okay.
like entities, attributes, relationships, that sort of thing.
Okay, so break that down for me a bit.
Sure.
What are entities in this context?
Entities are basically the main things
Right.
that we want to store information about in our database.
Mm.
Think of them like the nouns in a sentence.
Yeah.
So for a university database, some entities might be student, instructor, course, or department.
Got it. So entities are like the main categories.
Exactly.
What about those attributes you mentioned?
So attributes describe the characteristics of an entity.
Mm-hmm.
They're like the adjectives that give you more detail.
Okay.
So for the student entity, you might have attributes like student ID, name, major, enrollment date, things like that.
So attributes are like the specific pieces of information.
That's
if
it,
we
yeah.
want to store about each entity.
Right. And then we have relationships.
Oh,
And those show how the different entities are connected.
so it's all about the connections.
Yeah, think of relationships as the verbs in our database sentence.
Yeah.
So a student might enroll in a course,
Right.
an instructor might teach a course,
Uh-huh.
and a department might offer several courses.
Okay, I can definitely see how this visual approach would help.
Yeah.
It's like a map of all the relationships between different pieces of information.
Yeah.
So how do those relationships actually work in an ER diagram? Like, how are they represented?
Well, we use different types of lines and symbols
Okay.
to represent different kinds of relationships.
Hmm.
For example, let's say you have a one-to-many relationship,
Okay.
like one instructor teaching multiple courses.
Right.
We would show that with a line connecting those two entities
Mm-hmm.
with like a crow's foot symbol on the course side
Okay.
to show that one instructor can be linked to many courses.
That makes sense. It's a really clear way to visualize it.
Right.
The source you gave us mentioned weak entity sets.
Oh, yeah.
What makes an entity weak?
A weak entity set is basically one that can't exist without a corresponding strong entity.
Hmm.
So think about a section of a course.
Okay.
It can't exist without the course, right?
Right.
The section depends entirely on the course being there.
So the weak entity, the section, relies on that strong entity, the course, for its identity.
Exactly. It's like how a chapter in a book can't exist without the book itself.
Makes perfect sense.
Now, ER diagrams can also show these things called specialization and generalization,
Okay.
which help us model different levels of detail in the database.
Can you give an example of how those work?
Sure. Let's say we have an entity called person.
Okay.
Through specialization, we can then create these sub-entities like student and employee, and they would inherit attributes from that person entity,
Okay.
but also have their own unique attributes.
So a student would inherit things like name and address from the person entity,
Right.
but also have major and student ID as its own attributes.
Exactly. And generalization works the other way around.
Okay.
So if we have instructor and secretary entities, and we realize they share some common attributes like
Right.
employee ID and salary,
Right.
we can then generalize those
Okay.
into a higher level entity like employee.
Makes sense.
And that simplifies the model.
So specialization is like zooming in on specifics,
Right.
and generalization is like zooming out to see the bigger picture.
You got.
Love that analogy.
Now, another cool thing about ER diagrams is this idea of aggregation,
Aggregation. Okay.
where we can actually treat relationships as entities themselves.
Now, when would we need to do that?
Well, sometimes the relationships themselves have attributes or behaviors
Right.
that we need to represent in the database.
Okay.
So let's say you have a relationship like Proj Guide,
Okay.
which means an instructor is guiding a student on a project.
Mm-hmm.
But we also want to store info about each instance of guidance.
So like the feedback they give.
Exactly. Things like the evaluation date, feedback provided, all that.
So in that case, the Proj Guide relationship becomes something we want to track and store data about.
That's right. We can aggregate that relationship
Okay.
into a new entity, maybe called evaluation,
Okay.
and give it its own attributes like evaluation date and feedback.
It's like the relationship itself becomes important enough to be its own entity.
Exactly.
This is so cool.
And the best part is that once you've created an ER diagram,
Right?
you can translate it.
Right, into actual code.
Yeah, into a relational database schema, which is basically the blueprint for building the database tables.
So we go from a visual brainstorming tool to the actual structure of the database.
Exactly. Entities usually become tables, attributes become columns,
Okay.
and relationships are represented either as separate tables or as those foreign keys we talked about.
It's fascinating how it all comes together.
It is.
Now, I know the design of a relational database is crucial. What are some key principles to keep in mind?
One of the most important things is to avoid redundancy.
Redundancy. Okay.
Imagine a music library database
Okay.
where you store the artist's name and genre with every song they recorded.
Seems like a waste of space.
It's super inefficient, prone to errors.
Yeah, it's like writing the same information over and over again.
Exactly. That's where normalization comes in.
Normalization.
Yeah. It's a set of guidelines for how to organize data into tables
Okay.
in a way that minimizes that redundancy and ensures data integrity.
So normalization is like streamlining and organizing.
You could say that. It's like spring cleaning for your database.
I like that.
Getting rid of duplicates, making sure everything's in the right place.
And are there different levels of normalization?
Yes, there are. And each level adds more rules to further refine the database structure and avoid potential problems.
And all of this comes back to those functional dependencies, right?
Exactly.
Making sure we understand how different attributes relate to each other.
Absolutely. They're at the heart of normalization.
Okay.
For example, in our music library, we can say that an artist's ID
Okay.
functionally determines their name and genre, meaning we only need to store that info once in the artist table.
Right.
And can then use the artist's ID as a foreign key in the songs table.
To connect each song to his artist.
That's the idea.
So by understanding those functional dependencies,
Right.
we can avoid that redundancy and make sure each piece of information is only stored in one place.
Exactly. It's much more efficient and less prone to errors.
This makes so much sense.
Normalization is really key for good database design.
Yeah.
It helps us create databases that are efficient, reliable, and easier to maintain.
I'm with you on that.
Good.
Now, I'm curious about what lies beyond the relational model.
Okay.
The stuff you gave us also mentioned other data models like object-oriented and semi-structured.
Right.
Are these just like different approaches to organizing data, or do they serve entirely different purposes?
That's a great question. While relational databases are super successful and still the dominant approach,
Yeah.
These other models have emerged to address specific needs
Okay.
and handle different types of data.
So it's like having different tools in your toolbox.
Exactly.
Each one's suited for a particular job.
That's a good way to put it.
What about the object-oriented model?
So object-oriented takes inspiration from object-oriented programming
Okay.
and lets you represent data in a way that closely mirrors real-world objects and their relationships.
Oh, I see. So it's more about representing things as that they exist in the real world.
Right. So let's say you're building a database for a hospital.
Okay.
Using an object-oriented model, you could have an object for patient with attributes like name, address, medical history,
Okay.
and then create more specific objects like inpatient or outpatient,
Gotcha.
which inherit the attributes from that general patient object,
Right?
but also have their own specific attributes and behaviors.
So it's like a hierarchy of objects,
Yeah,
each inheriting characteristics from its parent, but with its own unique properties.
precisely. It's a great way to model complexity and make the structure more intuitive and flexible.
That's really interesting. How about semi-structured data models?
So semi-structured data models are all about handling data that doesn't fit neatly into rows and columns.
Okay.
Think of things like social media posts, sensor readings, product reviews.
Right.
This kind of data has a more irregular structure,
Mm-hmm.
and it can be tricky to represent in a traditional relational database.
So it's a more flexible way to store data.
Right. That doesn't conform to a rigid schema.
Okay.
One popular example is JSON,
Jason.
which stands for JavaScript Object Notation.
Oh, I've heard of that.
It's super widely used for web apps and APIs
Yeah.
because it's flexible, readable, and easy to work with.
So it's like having a more adaptable container for storing data.
Exactly. Semi-structured models are great for managing all that unstructured and semi-structured data.
That makes sense. It's definitely a growing area.
It is.
This is all incredibly interesting.
Yeah, it really is a fascinating field.
It seems like database systems are constantly evolving
They are.
to handle new challenges and harness the power of data in new ways.
Absolutely.
I'm also wondering how all of this fits into the world of big data.
Ah, yes.
It's a term we hear everywhere these days.
It is.
How do traditional database systems handle the massive amounts of data we generate now?
That's where things get really interesting.
Okay, let's hear it.
So while traditional databases are powerful, they can struggle with the sheer volume, variety, and velocity of big data.
Right.
We're talking data sets so huge and complex that they can't be processed effectively using conventional methods.
It's like trying to fit an ocean into a swimming pool.
That's a good analogy.
What's the solution then?
Well, that's where things like key value stores come in.
Key value stores.
Yeah. They offer a simpler, more scalable approach
Okay.
to storing and retrieving massive amounts of data instead of complex schemas and relationships.
Right.
They use a key to identify each data item, making it super fast to access.
So it's like a giant tagging system.
Kind of. They're really good for handling unstructured or semi-structured data.
Oh, okay, makes sense.
Yeah.
But what about when we need to do complex queries and analyses on all that data?
Then we bring out the big guns, parallel and distributed databases.
Parallel and distributed.
Yep. They distribute the data and processing workload across multiple machines.
Okay.
So they work together to handle the scale and complexity of big data.
So it's like having a team of computers tackling the problem together,
Exactly.
each one handling a piece of the data or processing.
You got it. This lets us break down those complex tasks into smaller, more manageable chunks
Okay.
and process data much faster.
So it's like having a supercomputer made of smaller computers.
Exactly.
That's incredible.
And distributed databases take it even further, spreading the data across multiple locations.
Which makes it more resilient, right?
Exactly. Even if one location fails, the data is still accessible from other places.
So that provides redundancy and fault tolerance.
That's it. It's super important when you need to design systems for big data,
Right.
where you need that high availability.
This is all so fascinating. It seems like the world of databases is just constantly innovating
It really is.
to address these new challenges and harness all this data.
Absolutely. And as we dive deeper into big data and these distributed systems,
Okay.
we run into really interesting things like
Yeah.
the CAP theorem.
CAP theorem.
Yeah. It basically highlights these trade-offs
Okay.
between consistency, availability, and partition tolerance in distributed systems.
Okay, that sounds intriguing.
Yeah, so in a nutshell, the CIP theorem says you can only have 2 out of 3 guarantees: consistency, availability, and partition tolerance.
And those are?
Consistency means that all the nodes in the system have the same view of the data. Availability means the system stays operational even if some nodes fail. And partition tolerance refers to the system's ability to handle network partitions where communication between nodes breaks down.
So you have to prioritize which guarantees are most important for your application.
That's the idea.
You can't have all three.
Exactly. It's a fundamental concept in distributed system design.
Okay.
And really understanding those trade-offs is crucial for building robust big data applications.
This is mind-blowing. Every step we take in this deep dive reveals more complexity and nuance.
That's true. The world of databases is full of challenges and amazing solutions.
And we've really only just scratched the surface here.
That's right.
There's so much more to explore, from column-oriented storage to query processing and optimization,
Yeah.
from transaction processing to database recovery mechanisms.
All fascinating stuff.
Wow, we could spend hours on this.
We really could.
But we've covered a lot of ground,
Yeah.
from data modeling basics to the challenges of big data.
Hmm.
I feel like I have a much better grasp now
Good.
of how these systems work and how they impact our world.
They're pretty crucial to how everything runs these days.
Yeah, it's amazing.
It is.
And you're right, there's so much more to explore.
Tons.
I'm actually really curious to learn more about those aspects you just mentioned,
Okay, which ones in particular?
like column-oriented storage and query processing.
Ah, good choices. Let's dive into those.
Okay, I'm ready. All right, so let's talk about column-oriented storage.
Okay.
How is that different from the way traditional databases store data?
So traditional databases store data row by row,
Okay.
kind of like you see in a spreadsheet, you know.
Mm.
But column-oriented databases kind of flip,
Yeah.
that they store data column by column.
I'm trying to picture how that would work. Why would that be better?
It might seem counterintuitive,
Yeah.
but for certain types of queries,
Okay.
especially ones that involve like analytical processing and data warehousing,
Mm-hmm.
column-oriented storage is actually way more efficient.
Can you explain why that is for those specific cases?
Sure, think about how analytical queries often work.
Okay.
They often need to access and aggregate values from lots of rows across specific columns.
Right.
So in a row-oriented database,
Mhm.
that means you have to read through all those entire rows, even if you only need a few values.
I see.
But in a column-oriented database,
Okay.
all the values for a particular column are stored together.
Right.
So the system can grab just the data it needs really quickly.
So it's like optimized for that kind of analysis.
Exactly. It's like the data is pre-organized for those tasks,
I like that.
making it much faster to access and process.
Well, and on top of faster queries,
Right.
doesn't column-oriented storage also help with compression?
Yes. It lends itself well to compression techniques,
Okay.
which can shrink that storage space significantly.
So faster queries and less storage space needed.
That's the idea.
Sounds like a win-win to me.
It is, and it just goes to show that there's no single best solution for every situation.
That makes sense.
It all comes down to choosing the right database tech
Right.
and storage methods
Mm-hmm.
for your specific needs.
Okay, so we've talked about retrieving data,
Right.
but what actually happens when we submit a query? Like, what's going on behind the scenes to process that and get the results back to us?
It's a good question. We kind of take it for granted that those results pop up almost instantly,
Yeah, it's like magic.
but there's actually a lot going on under the hood.
Really?
First, the system has to parse the query,
Okay.
which means it has to break it down into pieces
Mm-mm.
and figure out its structure.
So it's like translating from our language.
Yeah, exactly. From human readable to something the database system can understand.
Cool.
Once it's parsed, the system then validates the query
Validate.
in making sure it's grammatically correct
Mm-hmm.
and that you, the user, have permission to access the data you're asking for.
So it's like a security check,
That's a good way to think about it.
making sure everything's above board.
And once that's done,
Yeah.
the system comes up with an execution plan.
An execution plan.
Yeah. It figures out the most efficient way to actually go get that data.
Interesting.
So it looks at the size of the tables, indexes, the types of operations needed.
So the system has its own little strategy session.
I like that, like an internal strategist.
Uh-huh. Yeah.
And that whole optimization is super crucial,
Mm-hmm.
especially when you're working with these massive data sets.
Okay.
A bad query could take forever to run,
Oh, wow.
but a well-optimized one can give you results in seconds.
Big difference.
Big difference. It's like taking the scenic route versus the expressway.
And what about those different algorithms you mentioned earlier, like hash joins and things?
Oh, yeah.
Those are for optimizing specific operations, right?
Exactly. Those are just two examples
Okay.
of algorithms designed for efficiently computing joins,
Mm-hmm.
especially when you have those really big tables to deal with.
It's amazing all the work that goes on behind the scenes.
It is very intricate stuff.
To make something as seemingly simple as a query work smoothly,
Right.
it really highlights how complex these systems are
Yeah,
and the ingenuity of the people who design them.
absolutely.
Now, what about transaction processing and database recovery?
Ah, yes, those are crucial too.
Right, we touched on them before.
Mm-hmm.
Transactions make sure a group of operations are treated as one unit, all or nothing.
Exactly. So either everything succeeds or everything fails,
Right.
which prevents data corruption,
Yeah, that's super important.
And then recovery mechanisms are like a safety net in
Right.
case something unexpected happens.
Like a system crash.
Exactly. They allow you to restore the database to a safe and consistent state.
It's like a backup plan for your data.
You got it.
And don't these concepts get even more complex when we talk about parallel and distributed databases?
They do.
We talked about how those systems spread the data and processing across multiple machines.
Right.
But that must create new challenges, especially with coordinating everything and keeping it all consistent.
Yeah, managing consistency in a distributed database is definitely a big challenge.
So it's about making sure all those different machines have the same up-to-date information.
Exactly. Even when updates are happening simultaneously in different places.
Right.
And there are all sorts of approaches for tackling this,
Okay.
including things like two-phase commit protocols and consensus algorithms.
Wow, those sound complicated.
They can be,
Mm.
but they're essential for coordinating updates and ensuring everything stays in sync.
It's like a communication system
Yeah,
to make sure everyone's on the same page, even in a distributed setup.
precisely.
This whole deep dive has been incredible.
I'm glad you enjoyed it.
We've covered so much, from data modeling to query processing to the wild world of big data.
It's a lot to take in.
Yeah, it is, but I feel like I have a much deeper understanding now
Good.
of how crucial these systems are to our digital lives.
They really are the backbone of everything.
It's truly amazing.
It is a fascinating field for sure.
Well, thank you so much for taking this deep dive with me.
My pleasure. Always happy to talk about databases.
And to our listeners, if you're feeling inspired to learn more, we've got some great resources in the show notes.
Definitely check those out.
Keep exploring, keep questioning, and keep diving deep into the world of data. Until next time.
See you then.